Talking about Form 4 Physics, and our topic of discussion today is X-rays. I hope you remember previously when we were looking at cathode rays. One of the uses of cathode rays, we said they can be used to produce X-rays. Therefore, today I want us to discuss about X-rays. And I'm sure from wherever you sit, this is not the first time you're hearing of the word X-rays. You've heard someone say, I'm going to the hospital for an X-ray operation. Maybe a player got a fracture on the leg or on the hand, and you've heard them say, I have an operation in the hospital for an X-ray. Now, I want you to understand briefly that X-rays, just as part of introduction, X-rays was discovered by one of the German scientists when he was doing a research on the cathode ray tube. And what this guy discovered is, the cathode ray, we said, was a stream of what? Electrons moving from the cathode towards the anode. Now, this guy discovered that suddenly, when there was a target in the path of these cathode rays, some rays were produced, and these rays were of unknown nature. We could not tell what they are, unknown nature. And if we borrow from mathematics, I know if you take physics, mathematics is compulsory to you. Anything unknown in mathematics, we like saying, let it be X. So that is where the name X came from. X means unknown. That's how we call them unknown rays. They were unknown because at the time of discovery, their nature was not known. But later on, they were discovered to be produced when a metal target is placed in the path of cathode rays, or in the path of fast-moving electrons. Remember, cathode rays were just a stream of electrons. So this is what this guy discovered. Now I want us to look at few pictures. Look at your screen. What can you see? You can see just an example of an X-ray operation. You can see far up there is a picture. Someone's hand in the path of what? Of electrons. And on the other side, there is a picture of the same. Now there are two different pictures there. There's the real hand, and there's another one on the far right, which is a picture. That's exactly what happens in an X-ray operation. So we want to find out, maybe someone got a fracture on the finger. You cannot see this fracture using your naked eyes. So you have to do an X-ray operation. So you can see when this hand is placed in the path of the electrons, a picture is found on the other side on a photographic film. And if you look at the next one, that is what happens if you visited a hospital today for an operation, an X-ray operation. You will realize you are like this guy, there's an operation on the hand. So that hand becomes the object. Then there's the X-ray generator there, which is a machine. Then there's the X-ray detector. What happens? The streams of electrons will pass through the hand, but they will not pass through the bones of the hand. So a picture is formed on the screen, which we're labeling it as a radiograph. So the radiologist will detect that, will interpret this for you, and tell you where the problem is. So you can see X-rays are very important in our life. Now let's look at production. How are they produced? Production of X-rays. So we want to see, how are these X-rays produced? Now you realize that they are produced in the X-ray tube. So they occur where? In the X-ray tube. Just like we were talking about cathode rays being produced in the cathode ray tube, we are saying X-rays are produced in the X-ray tube. Now what happens? You realize when fast-moving electrons are suddenly stopped on hitting a metal target. So there are two things there. One, we have fast moving electrons. Fast moving electrons. And we have what we are calling a metal target. A metal target. So for us to produce X-rays, we need fast moving electrons. Then they are suddenly stopped when they hit a metal target. Now we want to look at the main features of an X-ray tube. So when you are asked to describe the production of X-rays, tell us they are produced when fast moving electrons are suddenly stopped by what? A metal target. Now where do they occur? In an X-ray tube. So in our next slide you will see the main features of an X-ray tube. You can call them X-ray tube features. An X-ray tube will look like that. In an exam situation, you are supposed to familiarize yourself with that picture, with that diagram there on the screen. You are supposed to know the main parts. If we start from the far left, you can see oil out and oil in. Then you can see some cooling fins there. Then there's the copper anode. Then on the far right, we have the heater circuit, the focusing cathode with a filament. Then there is the dark thing there, that is tungsten target, which is our metal target. And you can see a vacuum and an electron beam. When they hit the target, which is the dark object you can see there, we produce X-rays. We produce X-rays. So those are the main parts of an X-ray tube. You are supposed to familiarize yourself. We can ask you, we can label one of the parts as A, B, C, D with unknown letters and ask you to label them, to tell us which part is this, to name them. Then we can also ask you to explain the production of X-rays in the X-ray tube. So assuming that is the question, what will you say? Explain the production of X-rays in the X-ray tube. So how does the X-ray tube produce X-rays? So you are supposed to briefly say this. When current flows through the filament, so this is the procedure. We say current flows through the filament. Current flows through the filament, comma. When current flows through the filament, you can guess what happens next. When the current flows through the filament, we remember electrons will be produced by thermionic emission. So current flows through the filament, electrons are produced. Electrons are produced by thermionic emission. By thermionic emission. You remember thermionic emission meant due to heat. There is some heating there, heating effect of current. So we shall produce electrons by thermionic emission. Then what will happen to these electrons? The electrons are accelerated towards the anode. They are accelerated towards the anode. What makes them to move towards the anode? There is a potential difference between the cathode and the anode. So they are accelerated towards the anode. And in the anode, that is what we are calling the target. They are accelerated towards the anode or the target by the high potential difference between the electrodes, between the cathode and the anode. So the electrons are accelerated towards the anode by the high PD or potential difference between the electrodes, which means between the cathode and the anode. Then what happens? Their kinetic energy, since the stream of electrons, they are in motion, so they possess kinetic energy. So their kinetic energy is converted into other forms of energy. Remember, they are fast moving, so they have some kinetic energy. So their kinetic energy is converted into, now what do you expect? Electrons are fast moving and they are hitting a metal target continuously. That target becomes hot, right? Why? Because the kinetic energy is converted into heat energy. So most of this kinetic energy is converted into heat energy, and a small percentage and some percentage, a small percent, barely even 1% is converted to, and some percentage converted to X-rays, I mean, a very small percentage is usually about 0.5%. This is too small. So 99.5 of the kinetic energy of the electrons is converted into heat energy. This is a very important point to note. That means we are actually wasting energy, because we are producing 100% of kinetic energy, but on reaching the target, we only use 0.5. Where does 99.5 go? So it must be gotten rid of from the system, as we shall see in some of the special features of this cathode of this X-ray tube. So we are saying that if you're asked briefly, this is about 3 or 4 marks in a paper 2, section 1. It can also be in section 2. Some part of the question explain the production of X-rays in the X-ray tube. Then you write as a paragraph. You don't write as notes. So you say, when current flows through the filament, electrons are produced by thermionic emission. Then they are accelerated towards the anode or towards the target by the high PD between the electrodes. Then on hitting the target, the kinetic energy of the electrons is converted majorly into heat energy and some small percentage into X-rays. We have fully explained the production of X-rays. Now, look at that. If we go back to the previous slide, you see the cathode ray tube. I want to mention some important features of that cathode ray tube. I mean X-ray tube. Important features. I was checking through some past papers, and you can be asked a question or two on this. The key features of the X-ray tube. If you look at it, look at the cathode. What shape is that? It looks like a concave, like the reflector of a car head lamp or the reflector of your torch. It looks like that. Why? That is called a concave shape. So that cathode is concave shaped to focus the electron beam onto the target. It is not just flat, but we want to focus these electrons at a specific point on the target, so that we maximize on production of X-rays. Therefore, the cathode is concave shaped to focus the electron beam on the target. Look at that target again. Remember, electrons are hitting this target, and we have seen previously that 99.5 of the kinetic energy is converted to heat. What does that tell you? That we need a target made of a metal of a very high melting point. So some of the metals we need here are tungsten. So at the metal target, we need a target of a high melting point. And examples of this is tungsten and molybdenum. So we can ask you, why do we use tungsten as the anode or as the metal target? The reason is it has a high melting point to withstand the high heat produced at that particular point, because 99.5 of the kinetic energy is converted to heat. Therefore, this tells you that if we put there any other metal, what will happen? It will melt. So you will not produce any X-ray. Can you put there plastic? Plastic will melt even at a temperature of about 50. So it will just melt. So we need a metal of a high melting point, so that for a long time we can continue producing what? X-rays. You remember, if you visited a hospital, there is always a line. People are always on a queue. Those who want to carry out what? X-ray operation. So if you are using a metal of a low melting point, what will happen is, after one operation, the metal melts. So we need to replace it. That will be too expensive. Therefore, for our safety, we just use a metal of a high melting point, which is tungsten or molybdenum. You can think of another one. Then look at the also the anode is made up of a good heat conductor. If you look at that that anode, we have said at that point we are producing a lot of heat, but we do not need heat, we need to produce X-rays. Therefore, we need to use the anode made up of a good heat conductor. You can guess why. Why do we need a good conductor at the anode? For example, copper, to enhance dissipation of heat. So the anode, we need a good conductor of heat. And the reason is to enhance dissipation of heat. So we need to get rid of the heat away from the system, dissipation of heat. So we need to remove the heat, because we don't need the heat, but we need X-rays. Therefore, the anode is made up of a metal of good heat conduction. And an example of this is copper. Copper is a very good conductor of heat. Therefore, the anode, we need a good conductor of heat, which we are saying is copper. Then you can see also, just on that side of the anode, you can see some oil and something labeled as cooling fins. What is this for? So the cooling fins and the circulation of oil through the copper block will also enhance a further cooling. We require the system to cool after some time. So to enhance cooling, we need oil circulating. So the oil comes in, takes the heat away. So it's a circulation, continuous circulation of oil. Then you can see also that we have what we are calling the cooling fins. So those cooling fins and the circulation of oil at the anode enhances what? Further cooling. Then lastly, you can see that tube is evacuated. Why do you think it's evacuated? Evacuated means it is actually a vacuum. It is a vacuum. There is nothing in it. There is no matter. Why do we evacuate that tube? You can see it is sometimes it is called a glass envelope. Sometimes we just say a vacuum, or we say it's an evacuated tube. Why is the tube evacuated? To minimize collision of electrons with matter. So we have said also the tube is evacuated. It is evacuated to minimize collision of electrons with matter, where matter in this case could be gas or liquid or any solid. In that case, we want to minimize the electrons interacting with any other thing, because that will interfere with their movement to the target. Then, so we are waiting for X-rays and the electrons did not reach the target. So what will happen? We shall not have anything happening. We shall not have our X-rays produced. Therefore, we ensure the tube is evacuated to minimize collision of electrons with matter. Now quickly, we can move on to properties of X-rays. Properties of X-rays. If you check your KLB Form 4 textbook, you realize there is another topic called electromagnetic spectrum, EM spectrum, and X-rays is a part of that EM spectrum. Therefore, most of the properties of all other waves, some of them are also possessed by what? By X-rays. And the first one is they have no charge. So the first property, they have no charge. Why do they have no charge? How do we tell actually they have no charge? You realize when you pass a stream of X-rays in an electric or a magnetic field, there will be no deflection. If you compare this with the cathode rays were deflected in an electric and a magnetic field because they are negatively charged. Now here, the electrons that we are producing at the cathode, when they reach at the anode, we do not need the electrons, but we need their energy. So what happens? We will just take 0.5% of the energy to produce X-rays. So those X-rays have no charge. Therefore, they are not deflected in either electric nor magnetic field. That is property number one, no charge. Number two, X-rays penetrate matter. They penetrate matter. They penetrate matter. However, this depends on on the density of the material. So depending on the density of the material, we can use that's why the metal target cannot be any other thing. And if you look at the X-ray operation, whatever you place your hand or your leg on should not be any other thing, but it will be a material whose density is so high that the X-rays cannot penetrate, but they can penetrate through your flesh. Some of them, depending on their energy, can also penetrate through your bones. Therefore, we need to place your hand on a material of a high density, such that they penetrate through your body, but they stop at that material. That is how we shall get a picture of whatever is happening with your hand or your leg or your body. So depending on their energy and depending on the density of the material, they can penetrate matter. Then another one, the reason why we use X-rays in photography is that they affect photographic emulsions. That means if you focus X-rays on a photographic paper, they can make a picture for you. You've seen someone coming from an X-ray operation with a very big film because of the property of X-rays, which affect what? Photographic emulsions. That is why we use them in photography. Then they can cause ionization of air. They can cause ionization. They can just say can cause ionization. What is ionization? Now, these X-rays, as they are moving, if X-rays are moving and they come in contact with air, what will happen is they knock off air, and this air will get charged. Once air is charged, then we say the atoms are now ions. They are no longer atoms, they become ions. That process is called ionization. Because an atom is usually a neutral substance, no charge. But when it gets ionized, it means it will gain charge. So it becomes either negatively charged or positively charged. That's why we say when a stream of X-rays interacts with air, the air particles are knocked off. So in that process, some of the particles gain electrons, others lose electrons, and they end up being what? Ions. That process is called ionization. Then they can cause photoelectric emission. They can cause photoelectric emission. Now we will look at this later in a topic called photoelectric effect. Photo means light. So we are producing electrons due to light. So I remember telling you that X-rays are part of the electromagnetic spectrum. Therefore, they can cause photoelectric emission or photoelectric effect. We will look at that later. Then they can cause fluorescence in some substances. They are also electromagnetic radiations of a shorter wavelength than visible light. Then they have a wave nature. Maybe I explain something. They have a wave nature. Wave nature. What are some of the properties of waves? Waves can be plane polarized. Waves can be diffracted. They can be reflected, and many other properties of waves. So because they are wave in nature, they have a wave nature. That means they can be plane polarized and they can also be diffracted. So you can, if you forget about these two, just say they have a wave nature. Anyone who does physics will understand what you mean by that. So you don't need to task yourself and explaining so much, but you can just say they have what? A wave nature. And if I take you back to Form 2, when we were doing waves 1, there's the wave equation. Do you remember the wave equation? The wave equation back in Form 2, which was connecting velocity, amplitude, and frequency. And we were saying V equals to lambda F, like that. The wavelength of a wave and the frequency and the velocity. So our X-rays will also have, we will use this equation later. However, the next property tells us that they travel in a straight line with the speed of light. They travel in a straight line with the speed of light. That means, as we shall see their energy, we shall change where there is velocity, then we put the speed of light is usually denoted by c. So we shall see later that their velocity c is given by their wavelength times what? Their frequency. And c is usually 3.0 times 10 power 8 meters per second. So they have a wave nature. So this leads us to the next property, which we are saying they travel in a straight line with the speed of light. So they are very close to visible light in nature, as we shall see also in other examples. Now, before we look at examples, I want us to briefly look at their energy of X-rays. So can look at energy of X-rays. Do you think X-rays possess energy? Yes, that's why they can penetrate matter. So we are saying X-rays, they possess energy. But can you remember the energy transformations first in the X-ray tube? The electrons are moving with what? Kinetic energy. Then what produces all those electrons? There is a very high potential difference between the electrons and the anode. Then there is a heater filament, so there is a heater circuit. So there is a circuit connected to the cathode. Therefore, in other words, you realize that the kinetic energy of a bombarding electron will be equivalent to the electron charge times the voltage. So we shall say K is equals to EV, where E, this is electron charge, and V is the voltage. We have connected our filament to some circuit. So the voltage of that circuit, which is usually a very high voltage in K, like we can talk about 100 kilovolts. Kilo means 1,000. Or we can talk about 120 kilovolts, or we can talk about 200 kilovolts. So this is what we are calling the voltage, or the potential, the accelerating potential. Then E is the electron charge, which is usually 1.6 times 10 power negative 19. Therefore, the kinetic energy of the electron, which is Ke, is equivalent to what? 1 electron volt, or is equivalent to the charge of an electron times the accelerating potential. So you need to, those are the terms that we shall be using. When you see V, that means what? Accelerating potential. Then what happens when all the kinetic energy of an electron is used to produce X-rays? Then that means we shall produce what? X-ray energy. So all this energy, the kinetic energy, will be used to produce X-ray energy. So we are still saying Ke is equals to X-ray energy. This equals to X-ray energy. And remember, we have said X-rays are part of electromagnetic spectrum. Now, in that other topic, electromagnetic spectrum, you came across this equation here, that energy is equal to HF, where H is called Planck's constant, and F is the frequency of radiation. Therefore, I want you to get it clear. We are saying an electron will have kinetic energy, which is equivalent to what? E times V, the electron charge times the accelerating potential. And we are saying when this electron, most of its energy is used to produce X-rays, then we shall have X-ray energy. And X-rays are wave in nature, so they are radiations. So their energy is given by HF, where H is Planck's constant and F is what? The frequency of radiation. What does this tell us? This tells us that, therefore, EV, we are using EV because we know the electron charge, and we know the accelerating potential, you must be given. You will be told an X-ray tube operates at this potential. So we need to use EV unless you are given the kinetic energy. We don't know this because no one will tell you about the velocity of the electrons that were coming from the cathode. But you know the electron charge, and we can be told what? The accelerating potential V. So EV is equal to HF, like that. And you realize that if this energy from here, you realize if energy equals to HF, for us to produce maximum energy, E maximum, then we have to take Planck's constant times the maximum frequency. Because from here, from mathematics, you realize energy depends on the frequency of radiations, because H is a constant, just like the equation of a straight line. So our H here is a constant, therefore our energy depends entirely on the frequency of radiation. So replacing E max with EV, we shall have EV equals to Planck's constant times the frequency, which is maximum, like that. So this is one equation. You can use this equation. So if you are given the frequency of radiations, you can calculate any of this. You can calculate the accelerating potential. You can calculate this. You can make F max the subject of the formula. However, we want to relate this back to the wave equation. From the wave equation, and our wave equation is what? C equals to lambda F, where this lambda here is what? The wavelength. This is the wavelength of the X-rays. You realize we can make F the subject. So F will be equal to C over lambda. Now, what is the relationship between frequency and wavelength? This is an indirect or an inverse relationship. That means if we want to get F maximum, we have to take C over lambda, which is minimum. So if we want to get the maximum frequency, we take C, which is the velocity of light, over the minimum wavelength. This is a mathematical relationship where we say you can see F is 1 over lambda. That means they are inversely proportional. So if you increase the wavelength, you decrease the frequency, and vice versa. So I want to take this back here. I can call this one equation 2. I want to take equation 2 and substitute for F maximum. What would that be? You can try. So if I take from equation 1, EV is equal to H times F maximum. But we are saying EV is equals to H. What is our F maximum from equation 2? Our F maximum is C over lambda, which is minimum. So to get the maximum frequency, you take the velocity of light or of the X-rays divided by the minimum wavelength. So from here, we can conclude, therefore, that always EV is equals to, if I multiply this, you'll get HC over lambda minimum, like that. So this one will give us the maximum X-ray energy, a very important equation. We may use this in the next examples. Therefore, in an equation, use the appropriate equation based on the parameters given. If you are given frequency, you need to know how to use the frequency. If you are given wavelength, you need to know how to use wavelength. And I've told you before, E is a constant, so don't worry. This one is a constant, H is a constant, C is a constant. All these are constants. So what is the only thing that we want to look at? What varies will be V, which is accelerating potential, and the wavelength of the radiations. So all the rest are just constants, and you are always given in a equation. In KCSE, these constants are always given on top of the paper. So you need to check as you read the instruction somewhere, you'll be told use the following constants. So I had some student asking in an exam, we are not given C, we are not given this, but they are always given on the cover page, so you need to be very careful. Now let's look at some examples. Example 1. You can see it on your screen, so you can have some 30 seconds to read through example 1. You don't need to read the whole question, just write down the parameters given in our example 1 there. It says an X-ray tube has an accelerating potential difference of 100 kilovolts. What is the shortest wavelength in its X-ray beam? Then what are you given? You are given Planck's constant, you are given electron charge, and you are given velocity of light. So in that example, just note down what you are given. 1 more minute there. An X-ray tube has an accelerating potential difference of 100 kilovolts. So example 1 solution. In physics, you are supposed to write down. It's like you want to prepare some meal, so you have to write down a menu. But in the menu, you need to say, I need this, I need this, I need 2 cups of water, I need 2 teaspoonfuls of sugar. So you have the menu. So our menu in this case is 1, V. Accelerating potential was 100 kilovolts. So 100 kilovolts means 100 times 1,000. So that is 100,000 volts. Kilo means 1,000. So our V is 100,000 volts. What else are we given? Planck's constant, H. So H is 6.63 times 10 power negative 34. Then what else are we given? E is 1.6 times 10 power negative 19. And lastly, C is 3.0 times 10 power 8. What are we looking for? We are looking for the shortest wavelength. So which equation do you think we can use? We want the shortest wavelength. Which equation do we use? We can say from this EV equals to, we have 2 equations. So I want this to remain here. Equation 1 was EV equals to HF max. Then equation 2, we had EV equals to HC over lambda minimum. So I want this to remain here. You can copy them somewhere. And now I want to ask you, relating to what we have and the 2 equations, which one do we use? Do we use the first one? The first one requires us to look for F max because we have E, V, and H. No one is asking for F maximum. The second one, we have E, V, HC, and lambda minimum. And we have all these other ones except the minimum wavelength. Therefore, we use the second equation. So we shall say EV equals to HC over lambda minimum. Then we substitute. If we substitute, my E is 1.6 times 10 power negative 19 multiplied by V, which is 100,000. This should be equal to H, 6.63 times 10 power negative 34 multiplied by C, which is 3.0 times 10 power 8. All this is divided by lambda minimum. Then you can say over 1 and make lambda minimum the subject. So from here, if I multiply that side to make lambda minimum the subject, I'll have 1.6. I'll have 6.63 times 10 power negative 34 multiplied by 3.0 times 10 power 8. All this divided by 1.6 times 10 power negative 19 multiplied by 100,000. So what will be your answer? If you use your calculator, you get 1.24 times 10 power negative 11. Now, what does lambda represent? Wavelength. So what were the units of length in Form 1? Meters. So since all these are in SI units, there's no need for you writing the units here on each quantity, but the final answer must have units. If you leave it this way, it's incomplete. Therefore, you must say it is 1.24 times 10 power negative 11 meters, like that. This is our minimum wavelength. We can move to example 2. Example 2. I said we remain with these equations here so that we see what to do, which one to use when. Example 2 says the frequency of X-rays ranges from 3.0 times 10 power 17 to 3.0 times 10 power 19 hertz. Determine the range of the wavelengths, then the maximum energy of X-rays. Determine the range of wavelengths and the maximum energy of X-rays. Now, write down what you have. You are given C and H in brackets, very important constants. So that example 2, part A, we want the range of the wavelength. That means we need to get wavelength 1 and wavelength 2. Then that is what we are calling what? A range of wavelength. So looking at what we have, we can write down. We are given 1, the frequency, we can call it F1. F1 is 3.0 times 10 power 17. Then we have F2 as 3.0 times 10 power 19. What else do we have? We are putting down our menu. So what do we have before we prepare our meal? C equals to 3.0 times 10 power 8. Then lastly, H, Planck's constant, is 6.63 times 10 power negative 34. Therefore, part A of the question, we want the range of wavelength. Therefore, looking at these two, which equation do we use again? We have EV HF max. No one wants that. So we still want the wavelength. So we use equation 2. So if we use equation 2, that means we know that we have, in this case, our EV is equals to HC over lambda minimum. No one has talked about electron volt. No one has talked about accelerating potential. So you cannot use that equation. What does this mean? We need to use the wave equation. So the wave equation, which I want to take it as equation 3, that you must always remember, is C equals to lambda F, like that. So this is the third equation that we need. So in our example here, we are not told about the electron volt and whatever the accelerating potential, but we are talking in terms of frequencies C and H. Therefore, this tells us we need to use C equals to H lambda F. So from here, we can say from C equals to lambda F. If I relate this to F1, then I'll say C equals to lambda 1 F1, the first wavelength and the first frequency. Therefore, this one tells us that lambda 1 is C over F1, which is our C is 3.0 times 10 power 8 over 3.0 times 10 power, what was our F1? Power 17. Now this one will give us 1 automatically. 1.0 times 10 power 8 minus 17 is negative 9 watt. This is lambda, so that is meters. That is our F1. Then we go to our F2 and lambda 2. So using the same equation, we shall also say C equals to lambda 2 times F2. So this tells us that lambda 2 is C over F2, which will give us 3.0 times 10 power 8 over 3.0 times 10 power 19. So this gives us 1.0 times 10 power 8 minus 19 is what? Negative 11 meters. Now, no one told you to give the answers this way. The question was, give the range of the wavelengths of X-rays. So the range in this case, let me ask you a question. 1.0 times 10 power negative 11 and 1.0 times 10 power negative 9. Which one is bigger? Which one is bigger? And which one is smaller? So we realize that if it is negative, the higher the number, the smaller it is. Therefore, we shall say the range is 1.0 times 10 power negative 11 meters to 1.0 times 10 power negative 9 meters. This is the range. This is the smallest, this is the largest. Just like that. Part B. Part B is asking us for what? The maximum energy of X-rays. We want the maximum energy of X-rays. The maximum energy of X-rays. So we want maximum energy. So we have we have two options. We know we have already written somewhere maximum energy is equals to H times maximum frequency, like that. Since we already have our maximum frequency, we can use this directly. So this will give us H, which is 6.63 Planck's constant, times 10 power negative 34, multiplied by F maximum. So F, we had the one for 10 power 3 times 10 power 17 and 3 times 10 power 19. So if the power is positive, the bigger the number, the higher the result. Therefore, we shall take 3.0 times 10 power 19. If you use your calculator very well, then you should get 1.989 times 10 power negative 14. And what are we looking for? Energy. What are the units of energy? Joules. So you write there J. Very simple like that. The last example, example 3. The last example. Example 3. Still testing on energy of X-rays. Example 3. If we read together, the question says, in a certain X-ray tube, the electrons are accelerated by a PD of 12 kilovolts. Assuming all the energy goes to produce X-rays, determine the frequency of the X-rays produced. Then you are given H and E. So we write down what we have as usual. So what do we have in that question? One, we have the accelerating potential. So we have V. So you start V equals to 12. It's 12 kilovolts. 12 kilovolts means what? 12,000. So that is 12,000 volts. What else are we given in the question? In the brackets there we have H, Planck's constant, 6.63 times 10 power negative 34. And lastly, we are given E, electron charge, as 1.6 times 10 power negative 19. Then what does the question want? We want the frequency of the X-rays produced. The frequency of the X-rays produced. Now I take you back here to our 3 questions, which we said we must write them somewhere. In computer we say you copy this and paste in your long-term memory and format. Ensure you have a strong antivirus never to forget this. Therefore, look at those 3 questions. Which one do we use? Do we use the first one? Do we use the second one? 1 minute to think about that. The second one requires us to use wavelength. If you look at this, there's nowhere wavelength is given. And no one is asking for it. So we use the first equation. Therefore, EV equals to HF. Like that. F maximum. F max. Then we substitute directly. Our E is 1.6 times 10 power negative 19 times V, 12,000, equals to H, 6.63 times 10 power negative 34 multiplied by F. If you make F the subject, it means divide both sides by 6.63 times 10 power negative 34. Also divide this side by 6.63 times 10 power negative 34. So this one cancels this. Then you will have your F as, if you use your calculator very well, you should get something close to 2.9 times 10. If you look at that, that should be power 18. And frequency is measured in hertz, like that. So that is our, those are, I think those three questions can help you understand about energy of X-rays and the relationship between EV, then kinetic energy, and what have you. Now we want to look at hard and soft X-rays. So that directly tells you that we have two types of X-rays. We have hard, so types of X-rays. We are talking about hard versus soft. Now, why do we have two types of X-rays? For those who have gone for any X-ray operation, you will realize sometimes you are doing an operation that involves bones. Sometimes you are doing an operation that involves tissues. Therefore, the bones, the density of a bone and a tissue, they are not the same. The flesh and the bones, they are not the same. Therefore, if you wanted to do a scan or an X-ray operation involving lungs, you need X-rays that do not have a very high penetration power. They may affect you. So the machine will be set to produce X-rays of a lower power, which will only penetrate through your lungs, so that we can produce a picture and tell you what the problem is. But if it is about a fracture, we need strong X-rays that can penetrate through the bone and show us where the fracture is, if it's a dislocation or if that whole hand or whatever is, the bone is broken. Therefore, that results to two types of X-rays, hard and soft. So you may read more about it, but a common question will ask you to give us the differences between hard X-rays and soft X-rays. Therefore, looking at that table there, you see the first one, hard X-rays have a shorter wavelength, then the other one is directly opposite. Then these ones have a high penetrating power, a high frequency, produced by high voltage, produced by fast moving electrons, then used to detect fractures in bones. So the other side, you give the difference of exactly the opposite of what is for the hard X-rays, like they have a longer wavelength, low penetrating power, low frequency, produced by low voltage, produced by slow moving electrons. Then they are used to show what malignant growth in tissues as they are absorbed by such tissues, like tissues around the heart or the lungs or the liver. If you want to carry out an operation on those soft tissues, you need soft X-rays. So you need to ensure anytime you are told state the difference, you make a table, and whatever you write for hard X-rays, you give us a direct opposite. Do not use negations. Negations is like these ones have a shorter wavelength, then you say while these other ones have not. That is English. We don't need a lot of English. We just give us the opposite of the other. If you say shorter wavelength, the other one will have a longer wavelength. As simple as that. Then as we move towards winding up, what are the uses of X-rays? Where do we use these X-rays? What are the uses of X-rays? Where do we use them? Uses of X-rays. I've mentioned several in my examples, so you can guess. One, in medicine. So majorly we want to categorize them like this. We will use them in medicine. We will use them in industry. We can use them in security. Then we can use them in crystallography or crystallography. Now in medicine, when you hear of medicine, you've heard guys say, I'm doing medicine at KU or I'm doing medicine at UN. What does that mean? Medicine is just a huge discipline of knowledge. So in medicine, we will use X-rays, one, to diagnose and treat some diseases. That is number one in medicine. So if you are asked in an exam, you state uses of X-rays. Don't give medicine industry security. Give us the specifics. In medicine, what will you use X-rays for? Or sometimes the question can ask you, give 2 uses of X-rays in industry. So you need to be careful. But if the question is just a blanket, state 2 uses of X-rays, you have a choice of saying diagnosis and treatment of diseases. That is number 1 in medicine. Number 2, we can use them to treat tumors. You've heard of tumors. Someone has a tumor. You can still use X-rays to treat those tumors. Then we can also use X-rays to detect foreign objects in the body. A friend of mine, while working, was hit by a metal. Then the metal got lodged in his thigh. Now, it is very difficult for you to see where the metal is unless you take what? An X-ray. So an X-ray operation will actually tell you that this metallic object or a foreign object in your body is at this particular point. Take a case where someone swallowed a small pin by mistake. How can we locate it in the stomach? How can we locate that? We can only do that through an X-ray operation. So those are the 3 uses in medicine. Then in industry, we will use them to detect flaws in metal castings. We shall use them in welding and also to sterilize surgical equipment. Surgical equipment such as the blades, you can talk about the syringe, the needles, all those need to be sterilized before use. So they do not use the sanitizers that people are using. They do not use the surgical spirit, but they use what during manufacturing, because they are doing it in a large quantity, we will use X-rays to sterilize them. Then in crystallography, that is the study of crystal structures of substances. So different structures will behave differently when exposed to X-rays, and that will enable the people carrying out that study to tell us the exact structure, like of sodium chloride in chemistry. You remember the structure of sodium chloride in Form 2 chemistry. The person who came up with that structure was able to see that using what? Crystallography, which is another use of X-rays in industry. Then in security agents like airports, we will use X-rays to inspect hidden weapons in luggage. If you want to travel right now and you are at the JKIA, there must be a body scan and a luggage scan. So we want to detect whether you have something like a weapon by using what? X-rays. Then lastly, the dangers of X-rays. Dangers. So are all X-rays good? No. So they have some dangers. Dangers of X-rays. Now you realize that if you visited a hospital, the person operating the X-ray machine is always shielded, and is in that X-ray operation does not occur anywhere. It is in a special room. That special room is shielded from stray X-rays. Therefore, it is worth noting that if you get excessive exposure of living tissues to X-rays, they can get damaged. Therefore, you avoid it as much as possible. In fact, a lot of precautions are taken whenever an X-ray operation is to be carried out. If you are the patient, you will only have yourself and the operator. The people queuing for the operation are not inside that room, so that they are not affected by what? The stray X-rays, like that. Now we may look at one past paper question as I wind up. Just one past paper question. You can see it on your screen. Now the question says, the figure below shows the features of an X-ray tube. The figure below shows the features of an X-ray tube. Look at it. You have P and Q on the far left, then the filament, electron, beam, some part labeled A, X-rays, and some part labeled B, then the cooling fins and oil. After looking at that figure now, the first question is, name the parts labeled A and B. Name the parts labeled A and B. So we want to name those parts labeled A and B. So look at the figure again and try to guess what is A and what is B. Name the parts labeled A and B. So what is A and what is B? Looking at that figure, any guess, what is A? So looking at it keenly, you realize A is what? A, those are cathode rays. A, so your answer should be cathode rays. If not cathode rays, what are those? Those are just what? Electrons. You can say electron beam or simply electrons. So A, those are electrons. You can see from the cathode they are moving towards the anode. So that's a stream of electrons. A stream of electrons is called cathode rays. So your answer should be either cathode rays, electrons, electron beam. Choose one. Don't write this way in an exam. This means you had the marking scheme. So you do not write this, or just write one of them that fits you very well. Now, the next one, explain how a change in the potential across PQ changes the intensity of the X-ray produced in the tube. Explain how a change in the potential across PQ changes the intensity of X-rays produced in the tube. So you say the change in PD across PQ, what will happen? That will increase filament current, hence heating. Therefore, we shall have more electrons being produced, which will also affect the intensity of the X-rays. Now I want to look at a few questions from our viewers from wherever they are. Just a few questions quickly, then as we wind up. Joshua from Machakos, your question is, what are the impacts of X-ray on our body? We have said they can cause or they can damage soft tissues. So Joshua from Machakos, thank you. Tabitha Wanjiku from Kibudha Girls, will you kindly say why the cathode is concave in shape? Yes, we said it is concave in shape to focus what? To focus the electrons to the metal target. It's concave in shape. Concave is this shape actually. So when electrons are produced, all of them will move to the same point like that. I hope you got that, Tabitha. Then lastly, Joseph Kangede from Kilgoris Boys High School. Why is it difficult to verify the wave nature of X-rays by refraction experiment? Actually, it's very difficult because X-rays are not very true EM radiations. Therefore, we cannot look at them the way we look at light, because we need to produce them in an X-ray tube. So we may not be able to produce them like that. You know, like light, it's very easy to make light even using a simple